So we're going to start today with a basic introduction. This class is essentially about phase transitions. Phase transitions in almost exclusively Ising-like models. You could have a whole class on the Ising model if you wanted to. It's very deep. You can talk about CFTs and stuff if you wanted to. But here we're going to essentially just develop like a Landau theory, a phi-4 theory. Some of this material has overlap with 733, which I taught last year, except there's no quantum mechanics in this class. Okay, so it's essentially all classical stat phys. I'll talk a bit more about sort of specific goals, but let's just go through the course outline now. Phase transitions, order parameters, spontaneous symmetry breaking. I'll do that today and Friday. And then we'll look at mean field theory, which many of you have seen, and critical exponents. So today we'll talk a little bit about critical exponents and sort of the underlying concept of universality. So a big goal of this class is to discuss universality and sort of its origins in terms of a stat mech theory. So we'll touch on Landau theory, and you'll do Landau theory for, I think, a first order phase transition and a tricritical point in your first assignment. So this will just be a phenomenological theory. I'll describe what that is. And then we'll derive it with the Hubbard-Stradanovich transformation from microscopics. Okay, so that's one of the most important things we do in this course. We also do it in 733, basically for like a transverse field Ising model. But here we do a lot more than 733. So here we discuss perturbation theory, so fluctuations of the order parameter, and when that breaks down through dimensional analysis. We'll derive scaling, the scaling theory, including finite size scaling, which many of us use in numerical methods. And then we'll do probably a one-dimensional calculation in real space for real space RG. And then the Wilsonian RG is like momentum shell RG. Okay, so we'll basically turn to Fourier space and we'll discuss how we throw away different modes in Wilsonian RG. So Wilsonian RG gives us a framework to calculate critical exponents in the epsilon expansion. Okay, so it's epsilon is defined as the dimension you are away from 4 dimensions. And we'll calculate values for the critical exponents, and I think those, essentially the critical exponents for the Ising model will be the ones that you'll compare to your computational project. So you calculate them on your, with Monte Carlo on an Ising model in 2D, in 2 dimensions. And you'll compare to like the epsilon expansion. So that's a lot of that is Ising model up to that point. We'll talk a little bit more about maybe vector models and so on, but we'll really get into continuous symmetries after that epsilon expansion calculation. So we'll talk about Goldstone modes, lower critical dimensions, Mermin-Wagner theorem, nonlinear sigma model, which is this basically beginning of a field theory description of continuous symmetries. And the last part of the course, we'll develop the Kosterlitz, so both a phenomenological sort of topological theory of the Kosterlitz-Stalis transition as a vortex binding and unbinding transition. And we'll also look at the RG, the Kosterlitz RG equations for that, and discuss vortices and the role of topology. Okay, so that's relevant to this year's Nobel Prize, so I think it's kind of an interesting thing to end on. There's many texts. So Anton Burkov and I have developed this course over maybe 5 years or something. So we've written notes from all these different texts that I've listed here, basically in that order. Actually, maybe not exactly in that order. Nigel Goldenfeld's book, Lectures on Phase Transitions in the RG, it's got to be in the Perimeter Library. I mean, I assume. It's basically the standard text for this class. Everything's in there. Number 5, Nagel and Orland, I think also is one of the more detailed texts for what we're. So when you're in the nitty-gritty of calculations on the assignments, those are your 2 texts that are really going to like show you how to do calculations, basically. And by the way, for the assignments, you'll see questions that are in books. So, I mean, it's okay to work together and to use reference text and so on. Just fully reference everything. And these are, I think, Goldenfeld and Nagel and Orland will have a lot of the sort of details of the calculations that you'll be performing. Kardar, and so number 2 and number 6, especially number 2, that's the second volume of Kardar's StatMech books. The first one's sort of like 704, if you took 704, and the second one's like 705. That one I find lays out kind of the logic behind like the field very nicely. So it's a good reference, although it's very sparse in terms of calculations. You have to fill in the blanks. Nishimori and Ortiz, number 6, that's a new book that I like too. It has a lot of, again, it's laid out in a very logical way. Chaikin and Lubinsky does the momentum shell RG very nicely, I find. So it has a lot of soft condensed matter in it, which is cool. You'll use it, or I use it a lot for sort of Wilsonian RG. And it also has a very nice discussion of defects and topology and so on. So for the latter part of the course, you might want to look in Chaikin and Lubinsky. Carty's book, Carty's here next week, by the way. I encourage you to talk to him. He's giving a seminar on Tuesday. So his book is really, gives a really sort of intuitive introduction to scaling. So when we talk about scaling and we're setting up the RG calculation, I think Carty's book is the one that you're gonna use. Any questions on that? This course doesn't follow any one of these. It follows all of them or none of them. So you'll have to search around a bit to find what I'm talking about. Cool. That's it. That's all the organizational. The class is here. Don't go to the Alice room. Sorry about that email. I couldn't get the Alice room. Somebody has a book. So let's start with, like I said, let's sort of take it at an easy pace the first week here before everyone comes back from holidays. Some of the stuff I'm going to talk about, many of you will have seen before, but it's okay if you haven't. Okay, so we're just sort of, like I say, setting the foundation for what we're doing in this class. And by way of introduction, let's just discuss what we mean by phases and phase transitions. Symmetries, broken symmetries, phase boundaries, free energies, this type of stuff. So. Order parameters, symmetries. If there's one, I guess, question we're trying to answer in this class, it's essentially how do we go from a microscopic description of variables, of dynamics, of particles, where there's 10 to the 23 particles in a box maybe, and we have microscopic equations of motion, or a Hamiltonian or a Lagrangian or something that describes maybe the set of all position and momentum, whatever, QP. How do we go from that to a macroscopic description of properties, like collective properties? So say, how do collective properties emerge? Where the descriptors are no longer, momentum and positions of every particle I, but there's some sort of, there's some sort of macroscopic variables, like pressure, temperature, whatever, right? So, but this process, is I guess the central mystery of this class, right? It's very deep. It ties into complexity theory. I mean, you can imagine taking a whole bunch of particles and just putting the equations of motion on a computer. You can ask the question about how macroscopic variables or properties emerge. It's a very difficult question in general. It's computationally a difficult question, and even, like I say, in terms of a complexity theory standpoint, it's very difficult. So there's many different approaches that people have taken in order to make this connection, between microscopics and macroscopics. And this class only deals with the sort of a corner of that. That's which properties can be connected probabilistically. That's why it's StatMac, right? Why probabilistic? Well, first we have to frame the problem that we're dealing with, which generally is given, I guess, n, say, spins or particles or whatever microscopic species we're talking about. How do we calculate, say, an observable corresponding to an energy or something like that, free energy, say? And we'll often be dealing with binary variables or spins, which I'll talk a lot about. So a central problem might be to take a very simple many-body system and calculate something like the expectation value of an observable. I'll just write it in a general way that you might have learned from 704, say, where I'm counting over the number of states, omega, say EI. So this object, this expectation value of some observable, whatever it is, could be energy, could be magnetization, we'll deal with that a lot, involves this sum over all elements of state space. And so as you know, that sum is very, that sum is very big, that omega. So for example, if these spins were binary objects, so if it's up and down, or you can imagine a classical particle that has, can sit on n different lattice points, and it can be, each lattice point can be occupied or unoccupied. That's another two-state system. So the size of that state space, so for the quantum people, this is like the classical analogy to the Hilbert space, is exponential. And if you start thinking about how you might, I guess, enumerate all of the elements of that state space, if you just look at this equation here, I always remember, I think it's 260, it's something like 16, so I think it's 266. I think I wrote this down. 2 to the 266 is about 10 to the 80, which is the number of particles in the known universe. So, even just writing down or storing in memory, all of these elements that contribute to the sum is essentially infinitely complex. Right? It's an infinite number, essentially. It's impossible. It's an exponentially impossible thing to do. So these types of, solving this connection between microscopic and macroscopic has some fundamental infinity in it, or some fundamental exponential complexity in it. Okay, so this type of many-body class deals with an infinity in a very similar way that I think other interesting problems in physics deal with infinities. So there's different philosophies about how you deal with this type of infinity or how you make these connections, and emergence is one of them. Emergence is a separation of maybe length scales or energy scales, and saying that you have different theories at different scales and so on. So we won't deal with these philosophical questions. We're just going to deal with cases where we can make probabilistic connections. Okay, so that's basically the goal of 705. Who took 704, by the way? Okay. So 704 is ensemble theory and so on. So if you need to brush up on StatMech 1, the next 2 weeks is basically the time to do it. We'll start out by defining what we mean by a phase or a state in the macroscopic sense. Most phenomenon that you're going to deal with, say in condensed matter, fluids, quantum fluids, even other, StatMech systems, soft condensed matter systems, is a description of the states. It's a description of the low energy excitations that lead to collective behavior. Okay, this might not be obvious, but if you think about it, we're dealing with low temperature materials often. Low temperature materials have a ground state. You could call it the vacuum if you wanted to. And out of that vacuum, there's low energy excitations. And those excitations, interact and so on with different properties that give rise to collective behavior, which is really the interesting part often of low energy systems. So what collective means is, in some sense, it's the coordinated, this coordination or this interaction between many microscopic degrees of freedom, which are these low energy excitations. In this, part of this is a description of the transitions between different states of matter. So you might say that transitions arise out of these first two points. Transitions between different states of matter. We will develop this Landau-Ginzburg theory, which is a theory of fluctuations you'll often hear. What that is, in some sense, is imagine you're in the ground state of some, statistical mechanical system, and you put small amounts of energy in there. How does that energy lead to fluctuations of the spins or the occupations or something like that? And then the theory of those fluctuations often is used to give us a theory of the phase transitions. That's the sort of Landau-Ginzburg way. If you read up on the Nobel Prize, which you should all be experts on because you're interested in condensed matter, right? Then you'll know that there's other types of phase transitions that exist that basically don't fall in this, exactly in this sort of philosophy, but have to do with topological defects. And so with this list of, say, low energy states, or zero temperature states, say, vacuum states, low energy excitations, I would also put transitions to do with topology or topological defects, maybe. And I think if you kind of step back and follow how this course progresses, you'll understand why there was a Nobel Prize given in Kosterlitz-Salvis and other, Haldane type physics. It's because, you can almost give an entire class on this, what I would maybe call conventional framework. The low energy excitations. The theory of phase transitions, the RG, which is very successful. But what it leaves out is somehow this important point that there is phenomena in nature that are essentially tied to topological properties that are outside of this description. So I think from that sense, the Nobel Prize makes a lot of sense for us. That's pretty vague, but we'll develop this more. Things you need to brush up on. Stat Phys 1, like I said. So that's which is 704 type physics. That's ensemble theory, thermodynamics. Just know what a free energy is. Think about, canonical ensembles, partition functions, stuff like that. We will use classical field theories. So this is one of the tools that you need, stuff that we're going to develop. Will be the simplest classical field theories. we'll start motivating this by essentially Landau theories. Use of symmetries. You'll use known symmetries to construct Landau theories, or to construct field theories, which is sort of the philosophy behind field theories in some sense. We'll use different tools associated with perturbation theories of these. In some way of thinking, you have a vacuum state or a ground state at 0 temperature, and you want to see how low energy excitations contribute to perturbation theory. There's different ways to frame perturbation theories. We'll develop the renormalization group. It's one of the main goals of this class. I would say it's the main goal of this class, is to take these sort of philosophies and tools and develop the RG. And then we're going to compare the RG and what we get out of epsilon expansions, like I said, to computer simulations. So these will be your assignments. This will be your project. And depending on where you end up in your career, you might use a different proportion of these in your research, but I think it's very standard to sort of just teach the analytical theory in class and do, we don't have any sort of classes that aren't reading courses on computer techniques. But we could offer reading courses if people are really interested, which I should mention, I think we will do a reading course, right? You need a class, right? You guys might need a class. So we might do a reading course on, I'm not quite sure what it's going to be yet, but some type of computer simulation techniques and StatMech. So it won't run this semester. We'll put the grade on the books next semester. But if it's something you're interested in general, just send me an email, because when I start thinking about developing this over the next couple months, I'll try to tailor it to, I guess, what you guys want. States and phases. What do we mean by phases? What do we mean by ordering and broken symmetries? This is the starting point. Okay. Macroscopic matter exists in different phases, liquid, solid, gas. These are characterized by bulk properties. So response properties, things you measure in the lab, response functions. I'll give you the standard motivation that you'll read in textbooks of the liquid gas type transitions. There's for systems of particles at different temperatures, say. But we'll do most of our calculations on Ising model. So states are characterized by bulk properties. Things you measure. I'm on the right-hand side, thinking of bulk properties in the macroscopic system. And there's many different phases that you can imagine in theory and in experiment. And one of the big successes of last century's physics was sort of a rigorous way of classifying different phases due to symmetries. So in condensed matter, so the prototypical example would be solid, liquid, gas. What's the bulk property that defines a solid? What would you say it is?
Resistance to deformation under shear stress.
Right. Resistance to shear deformation. That's really it. That's the bulk property that you measure that defines a solid. A liquid has no resistance to shear deformation, essentially. Then what's the difference between a liquid and a gas? Right, so a gas also has no resistance to shear. Is there a difference? It's compressibility, right? Basic compressibility. And with compressibility, the idea that there's an interface. I'll just say compressibility. Oh wait, liquid is not compressible. Incompressibility, is that a word? So that's the bulk property. And the reason you might not have just, had these bulk properties jump into your head is, something like shear isn't useful as a general sort of underlying principle to define things that are, maybe not bulk solids, right? So these ideas aren't the ideas that we're generalizing. So for example, if I went away from a particulate system to a ferromagnet or magnetic system, so ferromagnet has a magnetization, so macroscopic magnetization. Right, it sticks to the fridge, presumably, in the absence of an applied field. And a paramagnet basically does not. No bulk magnetization. Of course, there might be some magnetization at some microscopic scale if you look at an individual atom or something like that. So again, these are bulk properties. Almost the last time we're going to talk about this, idea of, say, shear deformation or maybe compressibility in this class. But well, compressibility maps to susceptibility. If you map particle occupation to spin, so and susceptibilities, as most of you may already know, stuff like susceptibilities have to do with fluctuations of an order parameter, right? So we already see how these bulk properties are leading us to think of some sort of underlying way of categorizing these phases. So one we won't talk about a lot in this class, maybe only briefly at the end. There's a difference between metal insulator and superconductor. Again, very different than sort of a particulate system, itinerant particles moving around, maybe magnetic species that live on a lattice in a solid. Metal insulator, superconductor. So metal has a finite conductivity in the bulk. That's what I would say. Whereas an insulator has a zero conductivity. What about a superconductor? What defines a superconductor?
It's an ideal conductor and a perfect magnet.
Right. So it has zero resistance and expels magnetic fields. So zero. I'm going to go with 1L. So these types of bulk properties, in principle, you can calculate, in some cases, microscopically. And the fundamental idea is that, again, these look very different, but the underlying principle behind them all can be tied to this idea of Landau. That these macroscopic properties are a consequence of some sort of ordering, first off, or absence of ordering. So the microscopic properties distinguishing all these different phases, I'll say. Ordering and disordering. So shear deformation, as you know, is somehow related to ordering, and there's, whatever that ordering is becomes disordered in a liquid, say. So maybe not obvious how those properties connect, but Landau's idea is that they do connect somehow to ordering that we could discuss in the microscopic case. So this idea of ordering is the conceptual sort of basis for the theory that we're developing, ordering, disordering, and so on. But also be aware that exceptions exist. Nobody calls it the theory of ordering, but that's what I'm calling it. But exceptions exist to the simple theory of ordering. Stuff gets more complicated, especially when you think about strongly interacting systems, things like fractional quantum Hall. If you go on from this to do research, say in condensed matter, you'll often be working on the exceptions to what you see in this class. Okay. So just be aware that things outside of the paradigm that we're learning today exist. So now we have to define what ordering means. Right? I still haven't connected somehow microscopically, perhaps, what's going on with ordering to say something like resistance to shear deformation. Right? And that's where the concept of symmetry comes in, and symmetry breaking. So the way I would think of a broken symmetry is perhaps that maybe phenomenologically you might imagine at some high temperature, you expect all the symmetries of, say, the underlying theory to be obeyed. And as you cool the temperature down towards, the ground state or the zero temperature, low energy state that we're interested in, these symmetries somehow break down. Or the system that you're looking at no longer has the same symmetries as it might have at high temperature. So that's a very sort of experimental perspective. You might also say that the microscopic, because we're going to build up microscopic theories. So the microscopic laws governing motion have a set of symmetries. They're invariant under symmetry transformations. And that invariance somehow gets broken down. And that breaking of symmetry, if you will, corresponds to the ordering. So the underlying laws, maybe it's a Hamiltonian, some sort of equations of motion that you derive from it. So maybe it's Galilean, maybe it's just Galilean invariance, right? For a set of itinerant particles in the continuum. The sort of fundamental symmetry would be, translations, rotations, and boosts by a velocity or something like that. That can be broken down. So Galilean symmetry can arise from the underlying laws. However, a state of matter could, change under the same symmetry operations. Change means losing its invariance under the same symmetry transformation. So in our examples, just to state a few, we know the underlying symmetries that are somehow broken. So for a solid, this idea of Galilean invariance is essentially broken, because we know that the microscopic reason for resistance to shear deformation is the fact that maybe atoms arrange on a lattice, for example, and that lattice breaks translational symmetry. I'll just state a few of these. Again, rigidity arises from ordering into a crystal lattice. Of course, this is just one example of a solid. You could have a glass, which is amorphous. It doesn't have a crystal lattice, right? So somehow that rigidity arises from this ordering into a crystal lattice. And that crystal lattice breaks Galilean invariance. However it looks, maybe it's a square. How do you spell Galilean? Galilean invariant. You can't translate this atom here, or you can't translate your reference frame from here to here and see the same physics. Because here there's an atom, and here there's not, right? A ferromagnet, just another case of ordering. Right, it breaks some sort of up-down symmetry. It breaks the equivalence of up-down. Let me talk what I mean by symmetry in a minute, but we're going to call that time reversal symmetry. Right, so a ferromagnet with a magnetization, the magnetization is a bulk property that arises from all of your microscopic moments pointing in the same direction, right? So when you break that symmetry of an underlying Hamiltonian that's invariant under up or down transformations. So we'll talk about a Hamiltonian that has terms like, you multiply, say, the SZ components of a spin on two sites, I and J. Right, so that fundamental invariance comes from the fact that you know, this type of term is invariant under a up-down rotation of spins on I and J. So when you break that, that's what results in the bulk magnetization. And oh, do you know why it's called time reversal, by the way? I think you can imagine this coming from, you know, you can imagine a individual spin coming from an imaginary current loop, right? So you have a little current loop, I, and, you know, the field produced by I, which is like the degree of freedom, the magnetic degree of freedom, which we're manipulating. Maybe it's called B or something like that. B or M or SZ or whatever you want to call it, right? I is dQd, the time derivative of the charge, right? So if you change the sign of the time, so if you change the direction in some sense of the current, right? So then you, by the right-hand rule, you change the direction of the field. So just that minus sign there. So if you haven't seen time reversal symmetry, just think of it like that. It's just the up-down symmetry of these ferromagnets that we're talking about. So just a note, I'll probably slip periodically into the language of group theory. And we're not going to develop any group theory in this class. But if you read these books, you might see mentions of U1 or Z2 or things like that. So the symmetry operations that we're talking about, maybe this translation, for example, off of a lattice site, or the flipping of this magnetic spin, can be organized by group theory. So translation by lattice vectors, in the case of say a crystalline solid. So for example, so formally, these translations, in the case of the crystal, of lattice vectors are symmetry operations that leave the density invariant. So there's only certain symmetry operations, not this one, but maybe a translation by one lattice spacing, which leave the density invariant. So you could say that crystal has a symmetry. There's certain translations which leave the density invariant. So that set of all lattice transformations forms what's called a group. And the crystal is invariant under operations of that group, just another way of saying this. Okay, so translations, you know, all these translations form a group, say. I won't define it here because we're not going to use group theory. We're just maybe going to run into the language from time to time. There's also symmetry operations that aren't translations. So imagine having a crystal of different, yeah, okay, maybe. So you have crystals of different symmetries. There's also special symmetry points around which you can, say, reflect, or you could rotate around a point. There's different reflection symmetries here. Maybe there's one, maybe there's another one there. So be aware that, even in crystals, which we're not going to talk a lot about, that's more of a solid state physics subject, but there's also point groups. These are called all these translations, rotations, and inversions for different crystals. Make another group called point group symmetries. If you ever do a Lanczos and you want to diagonalize something on a certain finite size lattice, you have to reduce the Hilbert space by symmetries for the experts in the audience. So you do this through both translational symmetries, and if you really want to nail the problem to maybe fit a couple more sites in, then you also use the point groups of the lattice. So you also have to know which rotations and so on give you the proper symmetry operations, thereby basically reducing the size of the Hilbert space that you have to store. So these types of things come into play. For the ferromagnet, this time reversal symmetry is a realization of the simplest discrete group Z2 or Z2. It's called Z2 because there's two elements, the identity and some object or some other element that squares the identity. So another realization would be like integer addition modulo 2. So you might run into other types of models, that we're not going to discuss in this class. I wrote down a simple interaction for an Ising model, but you might also have different types of clock models. You can imagine integer addition modulo 3, 4, 5, 6. That defines different discrete groups. Okay, so we run into these from time to time. So we might say a Hamiltonian's invariant under Z2. If you hear that language, all it means is, a Hamiltonian has the symmetry of, I'm going to write the Ising model ad nauseum, we'll see it. But the Hamiltonian can have a Z2 symmetry, and that symmetry can be broken in the ground state. It's just a more general way of saying maybe time reversal symmetry or up-down symmetry, depending on whatever language you like. The discrete groups, we use discrete groups for many of the types of Ising calculations we're going to do in this class. But there's also, be aware, continuous groups. And, XY magnets, Heisenberg magnets, if you're used to dealing with these types of things, can be invariant, or they can break symmetries related to continuous groups. Okay, so. The one we'll deal with most is, these are mostly relevant to magnetism. But also to things like superconductors and superfluids and so on. So the most important continuous group is rotations in a two-dimensional plane. So if I had an arrow in the plane of the chalkboard and I could rotate it continuously by any angle. So if that was a fundamental symmetry, then that system would be invariant under O2. O2. So XY magnets are the prototypical example. But also, since a 2D vector in the plane, maps to the phase of a complex number, then O2 is isomorphic to U1. So you might also hear broken U1 symmetry. So if this 2D vector is, say, representing a complex wave function, which is the transformation of the phase. So superfluid helium goes from a normal fluid where the phase of the wave function has, if you will, plane 2D XY symmetry. Okay? And that symmetry is broken as you go into the superfluid phase. So there's a global breaking of a U1 symmetry you'll often hear for a superfluid. So as you cross that transition, there's a very definite idea of the broken symmetry of the phase. In a superconductor, it's basically the same thing. You have long-range phase coherence, and the phase of that wave function breaks U1 gauge symmetry, just gauged U1 symmetry, which means local in some sense. Okay, so this is relevant for superfluids. So the point of this is that even the most exotic quantum, or some of the most exotic quantum phases of matter that you see macroscopically, the source of all of their properties, zero resistance, Meissner effect, are somehow tied to this microscopic idea that on some level you have a symmetry breaking. Okay? And it just happens to be a symmetry involving the phase of the wave function. But this paradigm, the Landau paradigm, they often call it, that you have symmetry operations, you have invariance of systems, and then non-invariance of systems that correspond to broken symmetries. This also applies to superfluids and superconductors. So they're not exotic in this sense. They're conventional. They fall within this. We could develop this course from the perspective of superconductivity if we wanted to. That's all the group theory you need to know. Just those, that nomenclature essentially. So in all these conventional cases, the degree of ordering is quantified by what's called an order parameter. Okay, and that order parameter is a physical quantity that's based or derived from the broken symmetry. So this class will be a study of order parameters in some sense. The order parameter is just some object that's zero in a disordered phase, and it defines order essentially. So for example, a liquid could have, the liquid is maybe more disordered than a solid by some definition which says there's an order parameter that exists here but not here. So it's just a quantity with which we essentially assign the degree of ordering. So this Landau paradigm, we used to believe that all phases of matter fell within this paradigm that they can be distinguished by different order parameters. So if you have some phase of matter, there's some order parameter which indicates I'm in that phase. And if two phases have only the same order parameter and no different order parameters, then there's only one phase. That's what I'm trying to say. But I think fractional quantum Hall, which we're not going to talk about in this class, was one of the first examples where people realized that you can have the same order parameter or lack thereof in different phases. And then you need something maybe topological, for example, to distinguish different phases. So again, solid, just keep with our examples, because I'm going to drop these soon. Solid versus gas. Like I said, there should be an order parameter that distinguishes them. And in this case, it'll be a shear modulus. Or it could be a structure factor. So if you take a solid, you put it in a X-ray scattering apparatus, you look at the difference between a crystal versus a liquid or a gas, then you'll have Bragg peaks. At certain wave vectors, Q, in a structure factor. So just, that will give you another experimental, this is more of a bulk property. This is more of a scattering response. You'll get Bragg peaks at certain wave vectors in the solid, but not in the liquid or the gas. The liquid or the gas, so that's solid versus gas, liquid versus gas, can be distinguished by the density. That might be what you call an order parameter. In the ferromagnet versus the paramagnet, it'll be the magnetism, which we'll define. Let me just give the prototypical example of sort of a phase diagram for liquid solid gas. So just in this example, when I say phase diagram, I can imagine something that has some tuning parameters, maybe something we can tune experimentally, like pressure and temperature. And what a phase diagram is just a mapping of different regions of this plane, depending on where different order parameters are finite or where they're zero. So I can imagine somehow low temperature, I can order into a crystal, into a solid. And at high temperature, maybe low pressure, I might have a gas. So I might expect some sort of phase boundary. And actually, a prototypical phase boundary for solid liquid gas might look like this. So what I'm saying is maybe the shear modulus is finite here. You might get Bragg peaks in structure factor. You might have two densities here, one density of gas and one density for the liquid. And actually, a prototypical phase boundary will look like this, where you have a discontinuity up to some point. So let me explain this. So across a liquid gas phase boundary, a density is discontinuous. So we can construct an order parameter from the knowledge that we have this discontinuity. Okay? So something's going on in that boundary here. And if we take the difference of the density, which I'll call delta rho, we'll see a jump in, well, we'll see different behavior for this delta rho depending on, how we cut through this phase diagram. So we might be in the gas phase and we want to know the difference between the gas, the density where we are as we cut into the liquid. So, or vice versa. So this jump should go to 0 as we cross the boundary. Okay, so one of these is like a reference state, say the liquid. So the jump in density approaches 0 as we go across this boundary, only at this special point here. This is just an empirical fact that I'm telling you. It's called the critical endpoint. Otherwise, it's discontinuous. That critical endpoint is essentially the thing we're studying in this class. Like the only thing we're studying in this class is that critical endpoint. There's all sorts of other regions of this phase diagram that might be interesting. Maybe microscopically it's interesting what's going on in the phases. This I'll talk about later as a first order transition. But what we're really interested in is the special point where this jump in density goes to 0. And at that critical endpoint, again, this is just an empirical fact that I'm telling you. Say we fix, it depends on how we take paths through phase space, but imagine I fix the pressure and I'm just changing the temperature. Let me call P critical that point out here. And this is T critical. So if I fix pressure to the critical point, and I just vary delta P as a function of T, then what you'll find is, sorry, not P, rho. Then delta rho goes like a constant. T minus T, TC to T, TC minus T to some power. And imagine maybe I'm approaching it from above. So what that means is my order parameter, my delta rho, turns on. And it turns on in a very specific way. So let me plot delta rho versus temperature as I cross the critical point. So that curve will look like this. And that order parameter, if you will, diverges in a very specific way. Tc minus T to beta, where beta is what's called a critical exponent. And you can measure that critical exponent. And for the liquid gas transition, it's something like 0.32. And that's experimentally true. And it can also be calculated in theory. So it's just an experimental fact that the order parameter behavior near the transition, right, as I cut this way on my phase boundary, and my phase diagram, is governed by that equation. You could also study order parameters in different systems. Okay, so this is just a solid gas example. But also, if I look at the paramagnet to ferromagnetic example, which we're going to work on a lot in this class, I can imagine calculating a magnetization or measuring a bulk magnetization. Which I'll define next time. Let me just call it M. If you're an experimentalist, you know how this is measured. This magnetization is the order parameter because it's 0 above some transition and, you know, non-zero below it. So if I can have a phase diagram that is applied magnetic field versus temperature, just like my phase diagram there for the liquid gas. I would have a discontinuity between different magnetized states, which end in a critical endpoint at some critical temperature. And again, what we're interested in class isn't this region of discontinuity that happens near 0. It's this special critical endpoint. And at that critical endpoint, if you measure the magnetization as a function of temperature, so 0 applied field, so you're right here. What you would see is an order parameter that jumps at TC. Okay. And this is the paramagnetic phase, and this is the ferromagnetic phase. I should have wrote that here. Paramagnetic, ferromagnetic. So paramagnetic above, ferromagnetic below. The order parameter is what defines the ferromagnetic phase. And here you would see the magnetization jump as Tc minus T to the beta, to some exponent beta. And herein lies, again, the main point of maybe this class, is that for certain systems, and again, I'll explain what governs these systems, that beta, that critical exponent that's measured for this magnetic system, maybe it's something like an iron or nickel compound, is the same as the beta that's measured in the liquid gas system. So this is remarkably, and I think it's this is as close as I can get to doing an experiment in this class, just to tell you sort of the phenomenology that you would see in these types of experiments. And again, I kind of went through a lot. The idea that there's order parameters, we define order, we define phase transitions. I have to talk a lot more about phase transitions. First order and continuous. And just the idea that there's critical endpoints to phase boundaries that exist in different phase diagrams. And those critical endpoints have divergences, if you will. And it's not only in their order parameters, it's also in quantities derived from order parameters with fluctuations, like susceptibilities and so on. But those objects, the divergences that govern, say, the order parameters are exponents, which are the same in very, very different systems. And this is a reflection of what we call universality. Universality, arguably, is the most interesting thing in physics. Universality is what ties together all these different fields of physics that we study. It underlies the study of, say, quantum phase transitions and their relationship to classical phase transitions or classical critical points. Field theories, conformal field theories are just field theories that are derived for these critical endpoints. ADS CFT, right, where you try to take theories of critical endpoints and relate them to geometric theories in higher dimensions. This is all sort of a manifestation of what's called universality. And so this is the simplest experimental example of universality. And again, I think what we're trying to do in this class is derive or develop a theory of universality what universality means, what are the, I guess, features of a system, which symmetries and what, dimensional dependence different universal quantities have. What are different universal quantities? It's just some exponent that I've defined. Maybe there's other universal quantities. The relationship between universality and critical points. So this is really what we're studying. Universality arises because something special happens at that critical endpoint. It has to do with what's called the correlation length, which is something we're going to derive. It's tied to the existence of a length scale, or lack thereof. So there's some characteristic length scale that is basically defined by how the order parameter that two different regions or two different spatial positions are related. It's called the correlation length. What's that letter called? Xi? I should know this by my age. Whatever the correlation length. The correlation length is the fundamental object. Again, we're going to derive it from two-point correlation functions, but it diverges at a critical point. So just keep this in mind as we develop, as we get lost in calculations, over the next few weeks. One thing we're aiming at is an expression for a correlation length, and the idea that the correlation length diverges at these critical endpoints, which I'm just going to call critical points. The absence of a length scale is what gives you this universality. Not to keep you in suspense, this isn't a movie. The thing we're aiming for is a relationship, or to discover the relationship between some length scale, how we define a length scale microscopically, right, through relationships between, say, different spins, somehow in the ordered and disordered phase, and the relationship between that microscopic length scale which we've defined and these bulk properties which are universal. Okay. I'll continue next time maybe with a discussion of phase transition. So just an idea where we're going. Again, this is sort of very, hand wavy. What I'm trying to do is set the stage for the calculations that we're going to do in this class. So before we get to sort of microscopic calculations, I just want to discuss next class a little bit more about phase transitions. So all these boundaries. The relationship between phase transitions and divergences and singularities. And the idea that they're tied to singularities in the free energy of your system. Okay, that's what gives rise to bulk properties like magnetization or bulk divergences like you'll see in other properties. And then what we're going to go on to do starting next class is discuss the microscopics which lead to this type of phenomena right from scratch. And for that, we'll start with the Ising model. We'll define the Ising model. We'll look at calculations of the magnetization, and we're going to derive the mean field theory. And so this will be sort of the start of the concrete calculations, which will form the foundation for everything else that we do in this course. So we're going to take a very simple microscopic theory, the mean field theory of the Ising model, and we're going to derive that exponent beta in that mean field theory, which makes a bunch of assumptions. Okay, so again, phenomenologically, keep in mind, we talked about liquid gas density differences. We're defining what I mean by critical exponents. At the start of class, I'll define a few more critical exponents. But again, it's just a phenomenological definition. Okay, it's just an experimental observation that this behavior is observed. And because we can't do experiments in this class, we'll start with the Ising model. We'll derive the simplest theory, which is the mean field theory, and derive beta, and then basically go from there. Okay, so starting next week, we're going to get more heavy into calculations. So my apologies if this seems a little slow to start. But if anything here is just totally off your radar, then start reading now. Look at these textbooks, the reference text that I have here. Start reading the introduction, chapters in chapter 1, and just brush up on the phenomenology of sort of maybe phase transitions and phases and stuff like that. Because at some point in like a week or two, we're going to take all this stuff for granted, and we're going to be sort of knee-deep in calculations. So, okay, so see you guys on Friday. We're here. We'll probably go a bit later. We'll probably go straight between 10:30 and 12 for these classes, because I'm going to have to miss a couple classes during the semester. Who's going to the March meeting? A couple of you guys. So we'll probably cancel Wednesday's class during that week, which is sometime in March. And I'm not going to have makeup classes. I'm just going to go 10 minutes over every class, and then this will add up to a makeup class. And then, yeah, I'll bring your first assignment Friday, and you'll have 2 weeks to complete it. Okay, see you guys Friday.